Now, in order to understand the Faraday's laws and the Lenz's law, let's consider some illustrations. So in this question, it's given that we have a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. So let's draw the given directions. So if I consider this up as north, down as south, and that is east and that is west. So we have a plane that is in the east-west plane, means we have a plane here, and that plane is perpendicular to the screen you are looking at. So the loop is perpendicular to the plane and aligned along this east-west direction. Now it's given that a uniform magnetic field of 0.10 Tesla is set up across the plane in northeast direction. Now that's very significant. So he's saying that we have magnetic field in this direction, so that is northeast. This means this angle is 45 degree and this angle is also 45 degree. Northeast means it is the bisector of this north and east. The magnetic field is decreased to 0, means the magnetic field is changing in how much time? 0.70 seconds at a steady rate. Determine the magnitudes of the induced EMF and the current during this time interval. Okay. Now, in order to calculate the induced EMF, as we have learned in Lenz's law, that is equal to negative n. N stands for the number of loops. Change in the magnetic flux corresponding time interval, means the rate of change of magnetic flux with respect to time. Okay. Now here we have to look how much flux has changed. Now flux, the formula for the flux is B A cos theta. Now in the given situation, the normal to the loop, because the normal to the loop will be towards north, because the loop is in the vertical plane of east-west, so normal will be in this direction, right? And the magnetic field is making how much angle with that normal? 45 degree. So we know that the flux initially will be 0.10 Tesla. Area is how much? Because it's a square, so that is 0.1 meter into 0.1 meter. So that will be 10⁻⁻² meter square. Cos of 45 degree, so that is 1/√2. So from here you can very easily write that is 10⁻³ divided by √2. So that is the initial flux. Now in 0.70 seconds, that flux has become 0, and the number of turns here are 1. So we have only one loop, so we will say n is 1. Delta phi b, so the change in flux, the final flux is 0, because the final magnetic field is 0, initial flux, so that is 10⁻³ by √2. That is the change in flux, and the corresponding time interval is 0.70 seconds. So from here, what we can calculate, that this negative sign will come outside, that will become plus 10⁻³ under √2 times 0.70. So that under √2 is 1.414 times 0.70. So if you solve it, so you will get approximately 1 millivolt. So that is the value of the induced EMF. Answer is also written here. It is 1 millivolt. Now the next part is we have to calculate the current during this time interval. So induced current will be equal to induced EMF divided by the resistance of the loop. Here it is given what is the resistance of the loop, that is half ohm. So induced EMF is 1 volt divided by half ohm. So that will give you 2 milliampere. So that is our result. Clear? So this example illustrates that how will you use the formula for electromagnetic induction to calculate induced EMF and induced current. Now in this next illustration, here we are given with a circular coil of radius 0.1 meter. 500 turns are there and it has a resistance of 2 ohm. and that is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. So let's draw the sketch. So this arrow is representing south-north direction, and the horizontal component of Earth's magnetic field will be in this direction. So that magnetic field is equal to 3 into 10 to the power minus 5 Tesla. It is given here, right? And we are given with this coil, circular coil, and that is placed perpendicular to the horizontal component. So this means the coil is placed like that. So if you have an aerial view, you will just observe a straight line. Yet this is a circular coil, but it will observe as a straight line if you have an aerial view of the whole situation. Now this coil is perpendicular to the magnetic field. Okay. Now what is given? It is rotated about its vertical diameter through 180 degree in 0.25 seconds. So the time interval that is given is 0.25 seconds, means 1 by 4 seconds. Okay, and you have to rotate this coil. You have to rotate this coil. Now rotating that coil means what? See, initially if I consider the normal to the loop along this direction, whether you consider it as I cap or you can also write it as J cap, no issue. Now when you turn it through 180 degree, now that normal, unit normal will be in this direction. Now that becomes negative. This means initially the flux, the initial flux will be equal to B times A, because cos 0 will be 1, so that is BA, and the final flux is BA cos of 180 degree. Now cos of 180 degree is minus 1, so that would be minus VA. Now the change in flux, from here we can calculate the change in flux. That is the final flux minus initial flux. So that would be minus 2BA. So that is the change in flux. And that change in flux is happening in how much time? 1 by 4 seconds. So using this data, you have to estimate the magnitudes of the EMF and the current that are induced in the coil, right? So the induced EMF, you can write, that is equal to the change in magnetic flux per unit change in time, negative, and n is the number of turns. So negative number of turns here are 500, right? The change in flux is minus 2BA, and the corresponding time is 1 by 4 seconds. So this negative and negative will become positive. So this is 500 into 4 times 2. The magnitude of the magnetic field is 3 into 10 to the power minus 5, and the area of the coil, because the radius is given, radius is 0.1 centimeter, this is 0.1 meter, so that is pi r square. Pi means 22 by 7, r squared, so that is 10 to the power minus 2 meter square. So if you solve it, finally you will get 3.8 into 10 to the power minus 3 volt. So that is the induced EMF. Here it is given the answer. Similarly, if you want to calculate the induced current, so that induced current will be equal to induced EMF divided by R, the resistance of the coil. The resistance of the coil is given as 2 ohm, so that is 3.8 into 10 to the power minus 3 divided by 2, so that would be 1.9 into 10 to the power minus 3 ampere. So that is the answer, right? So I hope you have now understood that how to use the formula that we have generated for Faraday's laws of electromagnetic induction in these given situations.